Alright, welcome back to particle physics and the Standard Model. This is lecture 47, and last time we got a hold of the various mass orderings that were possible in the neutrino sector, right. So, we have measured only 2 of the delta m squareds using solar neutrinos and atmospheric neutrinos dominantly. So, that means we will have to choose a convention for checking what the actual mass ordering of the mass eigenstate spectrum should be, and we chose this convention. This is the convention chosen by everyone in fact, where you fix m2 squared to be larger than m1 squared, so that the sign of delta m12 squared is fixed, but you let the sign of delta m13 squared float, so that there are 3 observables, delta m12 squared which is positive, delta m13 squared, and of course the sign of delta m13 squared. And since the sign can take either positive or negative values, that leads to 2 different spectra that are possible. That is what I have drawn here. These inverted India flags are nothing but in each mass eigenstate how much admixture of the flavor eigenstates are present. That is what we are depicting here, that is why that is the legend that I have drawn down here, and the ordering in which the 1 is lower than the 3 is what you would expect. So, you know, that is the normal ordering, and then the ordering in which the 1 is above the 3 is inverted ordering. This is also called hierarchy. So, you have normal hierarchy and inverted hierarchy. Okay. And one important point to note is that the lightest neutrino could actually be 0 mass. We just do not know that. We just know, since we only know delta m1 squared, we do not know whether one of them is close to 0 or equal to 0, etc. Okay. And one thing is, we do know what the total mass of neutrinos should be. Actually, we do not know that either, but we have an upper bound on that coming from cosmology and the Catherine experiment, all of which point to a total mass of around 0.1 electron volts. And that would mean either the neutrinos, you know, because the difference in the actual mass between them is around 10 power minus 2 electron volts, either they are all sitting close to 0, so that they are all very squished down there, and then the maximum mass is only order 10 power minus 2 electron volt. Okay. That is possible, and something in between is also possible. And finally, the other extreme case where all the neutrinos are actually squished close to 0.1 electron volt, it is just that their separation is around 10 power minus 2 electron volt, that is also possible. Okay. So, we just do not know. Okay. As of now we do not know, and there are serious efforts underway to nail down at least the mass of at least one neutrino. And finally, we do not have to rely on just solar neutrinos and atmospheric neutrinos to measure the delta m squared using oscillations. We could also create our own sources of neutrinos, set our own baseline, build our own detectors, and measure oscillation probabilities. And that is what we do with reactor neutrinos, for instance. There are many sources that people use, but the most popular one is reactor neutrinos. Reactor neutrinos, as the name stands, as the name implies, is just neutrinos that come from atomic reactors. Okay. In atomic reactors, you cannot help having the weak interaction to get your fission, and so you are going to produce neutrinos copiously, and you can control them to some extent. Okay. What is the use of reactor neutrinos? You can cross verify the results you got from the natural laboratories of solar neutrinos and atmospheric neutrinos. So, that is what we are going to have a taste for today, and in particular I am going to highlight the result of the CHOOZ experiment. It is written CHOOZ, but it is pronounced CHOOZ. Okay. In France, this is a poster child for these kinds of neutrino reactor neutrino measurements, and they measured what? They tried to measure PEE. Okay. Remember what it is? So, I am going to go back to the 2 flavor approximation, which works especially for when you want to measure PEE. Okay. So, in this case they picked the baseline as about a kilometer. Okay, it is actually an order kilometer, the exact number does not matter, but the order of magnitude is a kilometer. And so what is PE? The probability of retrieving an electron neutrino after having produced an electron neutrino at the source, right, after propagation. That is the whole point of neutrino oscillations, correct. You do not get it back completely as an electron neutrino, there is only a probability for it, which is generically smaller than 1, right. Okay. So what was the result they obtained? I am going to draw the result. Okay. What are the unknowns here? One is delta m squared, right, that is fixed by nature, and the other is sin square 2 theta, this is also fixed by nature, both of these come from the Lagrangian, right, and the result goes like this. Okay, so let me mark off some points on this plot, that is one, and then this one is in log scale, alright. So let us call this is 10 power minus 4 down here, 10 power minus 3, 10 power minus 2, 10 power minus 1, 1. And what they got was, you would expect that got something like, this was what they measured and then probably it has an error bar, correct, but that is not what they got actually. Okay. They did not really nail down the delta m squared and the mixing angle. What they got was an upper bound on the oscillation parameters, but even that teaches us something. Okay. And the bound looks like this. So this has to be drawn a bit carefully. Down here at around 0.25, it went like this, and then near 10 power minus 2, you had some fluctuation, and that is it, and then we draw it like this. Okay. So what this means is, they said that they could not find the oscillation happening in the region above this line. That is what an upper bound means. Okay. In other words, to the left of this region is where they said the neutrino oscillation parameters had to be, that is delta m square and sin square theta. Okay. So let us try to understand that a bit. Alright. What happens if delta m squared is large? So we are over here in this region, up here. Okay. Go back to what this oscillation length is, if I can find it. Yeah, there you go. See, the oscillation length is in terms of delta m squared and E, right. It is basically E over delta m squared, remember. So, okay, here it is, E over delta m squared. So if delta m squared is large, that means you are in a regime where the oscillation length is much smaller than the baseline here, which is around a kilometer. Okay. If that is the case, then again remember, how does the oscillation probability go? It is like this, right? It is like this, and that is the oscillation length, right. So, and that, see, that is the oscillation probability. So if you only if your baseline is very small, if you only moved this much, okay, then you have not really seen much conversion happening, and that would mean that you are as yet insensitive to the amplitude, and the amplitude is what? Sin square 2 theta. Remember all this from 2 or 3 lectures ago, right? Go back to the expression for the probability. So here it is anyway. So the amplitude is sin square 2 theta, right? So that would what make you insensitive to the amplitude sine square 2 theta. Is that seen here in this plot? Of course it is seen here, right? That is why you have a straight line up here, okay, this straight line here. So let me mark it here, this straight line, right? This shows over here that you have become insensitive to sine square 2 theta, okay. So let me rewrite that, rephrase that, sorry, this is because now if L oscillation is much smaller than L, this goes to some constant value, right? And remember, this was the fast oscillation regime basically, correct? So I would set it to 1 minus sine square 2 theta over 2. In the fast oscillation regime, we said that this fast fluctuating sine square to half, right? That is what we are doing here. Okay, so how did you exactly get that bound over here? That came from, so they found that they could not quite measure it. They got a lower bound on the probability that the electron neutrino was retrieved as an electron neutrino, okay, and that lower bound on the probability was 0.95. So when you plug this in, you get a bound that is sine square 2 theta less than or equal to 0.1 approximately. So I have drawn it at around 0.2, but this is how you approximately get it, okay. If you do a full statistical analysis, you will retrieve the correct bound, okay. So that explains this area, all right, on the pink area that I have just highlighted. But if you were to set a short baseline, okay. So what I have drawn here actually over here in the beginning I said the baseline was short. I stand corrected. What I meant was this is the case with long baseline, fast oscillations, okay. That is the first case. Now suppose you set a short baseline, okay. Now is when we are looking at the short baseline. So this is the first case, this is the second case. Then, okay, if L is much smaller than L oscillation, what happens now? I can now take the argument, the sine square of the argument to be the argument square itself, correct? That is the limit, right? Because L over L oscillation is a small number, right? So I can write PEE equals 1 minus sine square 2 theta delta m squared. This turns out to be what I get when I put in the correct numbers down here, okay. This comes from the energy of the neutrinos being around 3 MeV. 3 MeV is not surprising. Remember, even in the sun we got MeV neutrinos, right? So every time you have weak processes like these, you get about MeV level neutrinos, okay. And this equation translates to a combined bound on delta m squared and sine square 2 theta, that is about 10 power minus 6. Okay. So that is what is depicted here, this region. Okay. All right. This is all inspection of the behavior of this plot, so that we are happy that we really understand the shape. But what does it all have to do with cross verification of the delta m square measurements? It is just that all of this is still consistent with atmospheric and solar neutrino data, right. How is that? We know that it has to be 10 for solar neutrinos, it is around 10 power minus 4, that is the delta m squared, and for atmospheric neutrinos it is about 10 power minus 3. I did not tell you what the theta should be for these two cases, but trust me, the theta is in the correct region, okay, for solar and atmospheric neutrinos. So, turns out all of this is still consistent, the upper bound is close to the real values, okay, on a logarithmic scale. Okay. So, now I am just going to quickly list out some experiments that study neutrino oscillations. There is no real physics involved here, but it is good to know what these experiments are, so that you can go and check, read about these experiments, read it on Wikipedia or read their technical scientific documents and so on, okay. But just so you get an idea of how people do this, okay, how people measure neutrino oscillations. So, one famous experiment is called LSND, and what they study is the muon neutrino going to electron neutrino. So, how do they get muon neutrino in the first place? They produce muons, they get muon decay and so on. Okay, we already saw how to get it from the atmosphere, right, pions hitting, pions being produced in a hadronic shower, right. So, similar considerations, okay. Then there is mini boon that also studies this, and very interestingly these experiments actually see some anomalies compared to the standard picture that we have just discovered. So, there are any number of opinions about whether these anomalies are true or not. It is a very interesting, very active field, and if you are curious, go read about these things. Then there is MINOS at Fermilab. Okay, they also do this, okay, but they do something interesting actually. They have two detectors, a near detector and a far detector. Actually, most of these experiments have a near detector and a far detector, okay. It is just exactly what it sounds like. There is a detector that is nearby, a few meters away, another detector that is probably hundreds of meters away, sometimes it is even many kilometers away, sometimes even hundreds of kilometers away, okay. So, the near detector actually looks for a new mu disappearance, okay, and the far detector is placed at the right distance close to the oscillation length, so that they look for the nu E appearance. Both of these could be measured, right, when a neutrino oscillates. So, they exploit both these signatures. There is Diabei in China. They do something interesting, they take electron antineutrino which goes to anything else. So, I believe it is a disappearance experiment and so on and so forth. Okay. There is also Dune that is coming up in the future, that is why I am writing it in red. Okay. Juno in China that is coming up in red, and so on and so forth. Okay. So, the question of neutrino oscillations is far from settled, okay, and oscillations is what you use to tell whether there is a fourth neutrino or not. Okay. So, it is a very interesting field, and I highly recommend you to go read up more about it. So, I will say a couple more things that are a bit historic here and enlightening also. Okay. So, firstly, one bit of history I think you should know for why all of this is not some exotic thing. We talked about the solar neutrino problem, right. So, the oscillation of solar neutrinos, okay, electron solar neutrinos to nu mu and nu tau, okay, were observed in 2001 in 2 different places. One was in the SNOW experiment in Canada, Sudbury, Canada, and another was in the Kamiokande experiment in Japan, and this experiment was led by a gentleman called Art MacDonald, and this was led by Takuaki Kajita. So, why am I writing these names? Because as recent as 2015, these 2 people got the Nobel Prize in physics for this. See, super relevant, super interesting, right. So, I had visited the lab in which SNOW is kept. It is 2 kilometers underground in Canada, Sudbury, Canada. So, now they have something else called SNOW Plus. It is an upgrade to the SNOW experiment, but nevertheless these are all very exciting times to be a particle physicist. Okay. Now, I will finally wrap up the module on the standard model with one last thought, okay, which is we talked about mixing in the quark sector CK matrix using the that came from the CK matrix. Then we talked about mixing in the neutrino sector, right, which was the PM-NS matrix, yes. And then we talked about in the quarks you do not always measure only the flavor eigenstates, sometimes you measure the mass eigenstates, and that is the reason why the mass eigenstates and the flavor eigenstates of charged leptons are the same, and that is why you put all the rotations in the neutrino sector. That is what we call the PM-NS matrix, because in neutrinos we only handle the flavor. So, that is clear already now, right. So hard to measure the mass. So, no use making use of the mass eigenstates in a practical setting, yes. So, one reverse question now can be asked: do quarks oscillate? We just saw neutrinos oscillating. What is oscillation? Mass induced flavor change, correct. So, through propagation the flavors, basically the flavor composition changes. Why can't this happen to quarks? Of course, you can also create quarks in their flavor eigenstate, right, nothing wrong in doing that, right. I can obviously start with some up quark in the flavor eigenstate. I know that it mixes, there is some up as I propagate up and charm and what top, right. So, with time as it as it propagates over a certain distance, as it evolves, I can get this. So, why do not we talk about quark oscillations? Okay. So, you can pause the video and think about this. It is very interesting and important to think about this question. I will give you the answer. It comes down to, because the quarks participate in strong interactions, okay, their propagation is rapidly stopped. They are not going to be propagating in vacuum or anything for long. You know that you cannot create in practical settings anyway, you are not going to create an up quark just like that. You are going to put it in some confined bound state to begin with, right. So, so even you might think of matter effects also just like in neutrinos, but again there at least there was a forward scattering in an electron background. Here you are not going to get anything like that. Okay, here you are just going to get stopped. You are already, the quark is already sitting in some confined bound state, and then the confined bound state like a baryon is going to see other baryons and just get stopped. Okay. Even otherwise, or another way to think about this is if you write the superposition in this way, yes, this is a coherent superposition, yeah, and if this combination is propagating, it better stay a coherent superposition, right. But then because it is going to encounter all these other nuclei, baryons and so on in a medium in which this is traveling, this combination is going to immediately decohere, right. So, you are not even going to hold on to this coherent superposition in the first place. So, then what is the point of talking about oscillations and retrieving quarks in some other flavor and so on. Okay, this entire structure would just fall away. Okay, remember decoherence in quantum mechanics, that is what is going to happen. You are going to interact with the environment and immediately decohere. Okay. So, for these reasons we do not talk about quark oscillations. Okay. In principle it is possible, but it just does not happen really in nature, and so it is useless to talk about it. Okay. All right. So, that brings an end to the module that I call deconstructing the standard model. So, we constructed the standard model using quantum field theory, then we built up all the ingredients, all the symmetries we put in, gauge symmetries and Lorentz symmetries, and then we broke it with symmetry breaking, yes, using the Higgs mechanism, and that gave rise to masses for the gauge bosons and the fermions. Not only that, because you had these masses, you also had mass mixing, and hence the CKM matrix and the PMNS matrix, which gave us neutrino oscillations, right. Good, that is what we have done thus far, and we will now move on to a whole new module of the course, which is probably what you had in mind when you registered for this course: particles hitting each other, decaying and all that sort of fun. Okay? Basically relativistic kinematics, which will put together with some dynamics. Okay? So, I am going to wrap up this lecture with some introduction of some basic things that you know, and we will take that up in the next lecture and put it into a collider context. Alright. So, let me just write down quickly one or two things that you already know to warm up, then we will take that up in the next lecture. Okay. So, the beginning of all this is a transformation. What is this transformation? Okay. So, what is this? I probably switched the indices. This is the Lorentz transformation, correct? So, if we take boosts in the x direction, how does it look like? It is this, and I am setting C to 1 as usual, what happens to the Py? That is Py, Pz is also unchanged, and finally in any frame there is an invariant quantity. What is it? This, what is this quantity? It is like the space time interval, except this is now called invariant mass when it comes to dynamics, correct. So, these are boosts in the x direction, and what is gamma? Gamma is 1 over 1 minus b squared. Just to, so you remember beta is what? Beta is the speed of the frame that you are thinking about, okay, the inertial frame itself, okay. So, technically it is v over c, but we are setting c to 0. Okay. So, I will stop here, and in the next class we will start using this for collisions, and we will look at various convenient frames in which we can think about collisions and what are the real life implications of them. Alright. So, I will stop here. Thank you. See you in the next class.